So again, today I'm sharing a picture from Paris. So I've been to Paris a few times for conferences, and I was invited to give a workshop there once also. So it's amazing the architecture and stuff that you see, and then you realize that this was all built on colonial funds. So this was built on money from the colonies, but that's what it is. All right, let's get going. We'll study today semiconductor materials and processing. So when we talk about semiconductor material, we can take silicon and learn about silicon, because when you look at devices, majority of electronic devices are made of silicon. And when we talk about silicon processing, almost all of the semiconductor materials are done same or similar processing. So we'll look at silicon, but having said that, other semiconductor materials would get the same treatment. There'll be slight differences depending on materials and depending on their physical properties, their electrical properties, their mechanical properties. But as we say, IT industry or in the industry for decades. In many of the homeworks I've seen, you guys have related how we are doing things today, the way we are today. So that tells me that many of you already are now familiar with silicon chips. Now, how do we use it? Silicon chip is basically a plate, if you can call it. It's a 0.5 millimeter plate, cut and round, and 99.99% silicon. When I say plate, we don't plate. When you become familiarized with the term, there are certain things that are related to wafer. They come in different sizes, all the way from 8-inch to now 16-inch. So industry uses big wafers, and they have dies on that wafer. So each wafer would then have squarish areas. So, and on one wafer, for industry, when they're making one type of chip, they will have different copies of those dies, exact copies. So in one processing step, same thing would happen on all the dies across the whole wafer. And that each die would be identical to the other die. And at the end, we cut it and we get the small things out of it. And when we get that small thing is then the die. Now we have, commercially, we have 32 billion transistors on one chip. And going from this bare silicon, like pure silicon, tens of creating a bunch of these billions of transistors and resistors and capacitors and all the things that would make up a circuit. So they all are built within the silicon wafer or on top of silicon wafer. Now, if you take semiconductor material, a semiconductor material is an element that is not a good conductor and that's not a good insulator. So their conductivity fall in between conductor and insulator. Why do we use them? Because by incorporating very small amount of impurity, we can dramatically change it to a very good conductor. Okay, I hear my voice is not coming okay. Is that the case? You cannot hear me okay.
Sir, it's lagging.
Or can you hear me okay? I hear a bunch of yes, yes.
Sir, at times it lags.
Can you hear? Okay, let me see if I can turn some things off on my computer. Let's give it a try now. Can you hear me okay now?
Yes, sir.
Turned a few
Yes, sir.
things off that might have been using network. All right. So we know the periodic table from high school chemistry. So in that periodic table, we identify group 4 elements, group 1, 2, 3, 4, 5. So group 4 elements are like carbon, silicon, germanium, tin, antimony, lead. So these are group 4. And we use them as elemental semiconductors. We use them without adding any other. We're not talking about impurity right now. We're just talking about bare semiconductor materials. Or we use group 3 and group 5 together. We mix them equal amounts and we use them and we call them compound semiconductors. If we use 2 elements, there would always be group 3 and group 5. Or they can be group 2 and group 6. And the reason will become evident soon. In group 4, the outermost shell, outermost orbit has 4 electrons. And there are 4 empty sides, right? To make it complete, we need 8 electrons. Now, when you talk about group 3, they have 3 electrons in the outermost shell. When you take group 5, they have 5 electrons in the outermost shell. When we use group 3 and 5 together as alloy, there's no chemical reaction going on, but we mix them. So they share their outermost shells. In that case, 5 and 3 come together and they make 8 shared by 2. That makes it, again, half empty in the outermost shell. We call compound semiconductors, and if there are just 2 elements, one from 3, one from 5, we call it binary semiconductor. But we can do another thing. We can take group 3, 1 element from group 3, and we can take 2 elements from group 5 also. But the condition is that total sum of group 3 and total sum. I saw a raised hand. All right, can you guys turn your video feed on? I cannot see all of you, but I see somebody raised a hand. Ahmed Imran raised hand. All right, go ahead.
Sir, so a binary alloy is made of only one conductor and one insulator.
No, they're all semiconductors. So what we are talking about semiconductors. When we mix group 3 and group 5, we get a semiconducting material. But now it can be gallium from group 3 and arsenide from group 5. So gallium arsenide.
You're saying something about binary?
So gallium arsenide is the semiconductor material. No, I'm not talking binary in terms of digital circuits. No. We call them binary semiconductor because 2 of them are being used.
If
there are 3 of them being used, we call them ternary semiconductor.
Okay. Understood.
Okay. Let me try something. In terms of digital circuit, it's binary, like 2 of them. If you use 3 materials to get compound semi, if you use 4, we call that quaternary, just to identify how many elements are being used to get the compound semiconductors. Right? Now, if you look at the examples, that would be aluminum phosphide, aluminum arsenide, gallium phosphide. So these would be 2 elements coming together to give us compound semiconductor. Now, why do we want to do that? Because when we get those things, we get different electronic or optical properties out of them. depending on our need. We look at the need, why we want to change material. If silicon is good for electronics, just stick to silicon. But by changing another material, we can make an LED out of it, which would mean it is an optical device now, or your flashlight, or your camera, right? So they all are optical devices. Now, when we use ternary, again, if we get one element or two elements from group 3, their total amount has to be equal to the element we get from group 5, right? Same would be if we have 4 elements, 2 come from group 3, 2 come from group 5, but their total amounts in their own groups have to be equal. Same for group 2 and 6, right? So 3 and 5 come together, 2 and 6 come together. Now, when we use compound semiconductors within one group, like group 3, we can have relative amounts different. Like here it is written aluminum gallium arsenide, but there is a subscript with aluminum, small x. And there is 1 minus x written with gallium. And 1 minus x just means that the total would be equal to the total amount of arsenic there. This makes sense? We'll talk on this later on when we talk about compound semiconductors. But that subscript X will tell us how much of aluminum is there, how much of gallium is there. But the total amount would be always equal to the total amount from the other group. Now, why silicon of all of this? The most fundamental reason why we use silicon is in the second homework. If you have already received second homework, the reason is they found that it was easy to create an oxide of silicon. Now, what is an oxide? Oxidation. Where do you see oxidation in everyday life?
Sir, I think
Rust.
channel length.
Rust.
Rust. All right, that's fantastic. When iron gets rusty, what does it turn into?
Iron
Ferrous
oxide.
Ferrous oxide, right? Ferric oxide, ferrous oxide, different name. So, and its properties, do the properties stays the same as iron? When iron oxidizes, does it have the same properties like iron?
No, sir, it changes.
It changes, right? It's if iron has magnetic properties, iron oxide does not have magnetic properties, right? It becomes powdery, mushy, right? So it can easily scrape up. So when oxidation happens, silicon becomes silicon dioxide. It becomes a very, very good insulator. So now silicon semiconductor, which we make a good conductor by doping, when it becomes oxidized, it becomes a very good insulator. And we have use of that insulator when we are making devices. We either use it to make a gate in transistor. So transistor has 3-4 important parts. There is source, there is drain, there is gate, and gate has a insulating layer called gate oxide. Or we can use it to just cover the whole chip to electrically isolate all the different components from each other, right? So that became a reason why we use silicon in semiconductor devices. Otherwise, there were choices of other oxides. So germanium used to be the material before silicon became more convenient to work. Now, silicon or any other semiconductor material is used exclusively for ICs, for integrated circuits. We make inside the chip, inside the wafer, we make on top of wafer. So hence we make this multi-layered ICs. And now when we talk about silicon, we don't use it in, we use it in very high purity, and we use it in a single crystalline form, single crystal. Now crystal or crystalline formation is a property which is unique. It takes us to the very precise atomic arrangement of atoms in a long range. So we have talked about example of diamond. It's carbon, right? We talked about carbon comes in other shapes also. But carbon, when it is really compact, when it has long range crystalline order to it, it becomes transparent, it becomes expensive, right? So the crystal properties of semiconductor materials are what define their physical, mechanical, electrical properties, optical properties, all of those. And for silicon, we need to know its crystal properties. We need to know its physical properties as well, right? So here's just a small table telling us some things that we can understand. For example, it's an abundant element. Where do we find silicon? Where do we find silicon?
Sand.
Sand, right? All around us. It occurs in the form of silica, right? Which is sand. But we have to purify it. And then we have to create crystalline structure out of it. And once we get crystal, it gives very good crystal, which is very strong and very hard. We can dope it where we introduce other elements in it. We can use silicon. It's oxidized from silicon dioxide to get protective layers, to get insulating layers. Then it talks about, on the right side, it says appropriate band gap. We haven't talked about band gap. My goal is we will look at what is band gap and why it is important. And there's another thing, it says mobility. Mobility is also another important property for semiconducting materials. We'll look at that as well. But ultimately, of silicon, physical as well as electronic properties that make it material of choice. Is my voice okay now? Are you getting any lagging anymore? Gigapascal. GPA is gigapascal. Pascal is a unit of hardness, or Pascal is force, and its unit of force, how much it can withstand. Now, when we say crystalline material, so crystalline material is something that has precise arrangement of atoms. And this is how it looks like in 3D. So the right-hand side is a 2D picture, is simplified, but the left-hand side is a 3D picture of silicon. Now, something you can note here is that each silicon atom has bond with 4 other silicon atoms. So hence, that thing about having 4 electrons in the outermost shell, but once they create these covalent bonds with each other, they share their electrons with each other, and hence their outermost shells are complete. They have 8 in the outermost ones. All right. Now, we call this arrangement, I'm going to use this word, which is used differently in the context of crystallography. This structure is called diamond structure. It has nothing to do with the diamond made of carbon, right? That's diamond in a layman term. In crystallography, this arrangement of atoms is called diamond structure, diamond lattice. We call it different ways. And what's interesting here is that each atom, we can clearly find its nearest neighbor. We can clearly and exactly find how far is its nearest neighbor and at what angle. Right? Why is that important? Because electrons have to travel when we are doing conductivity, right? When we are measuring conductivity, when we are using, the electrons need to know, jumping from one atom to other atom, which atom is the closest in that direction of the flow of conductivity. Now, let's take a structure. This is silicon's crystalline structure. What are other ways how materials exist in nature? There are materials which have no order. Same element, but it may exist that there is no atomic order to it. We call those materials amorphous materials, right? Just random atoms. Or there may be some materials, silicon as well, which may occur in a form where there is some crystalline structure and then it breaks where it is crystalline, and then there is again breaks down. Now, when we talk about that, we call those polycrystalline materials, right? So we use silicon also as in a polycrystalline form. We call that polysilicon in that case. So polycrystalline would be shortened as polysilicon or poly whatever material we talk about. So others is usually material expand on heating. How can we measure atoms distance which either crystal precisely? Now that's a very interesting observation. Crystalline materials have very tightly packed structure. Yes, they will expand, but we know precisely what would be the case. Even is are in, they are very, very tightly bound in that structure with each other. And hence that's expensive to get there, right? Hence to make this crystalline structure is expensive, and that helps us maintain integrity if there is, if in the case of thermal gradient or thermal change. Now, in the middle, there is two cubes which are shown to be interdigited kind of thing, interlacing in each other. So if you look at this, we get more into crystallography, and that's a specialized field in itself. So if you have this guy, there'll be exactly similar structure or box next to it, because that's the idea. It has to show this repetitive order going in the long range across the whole wafer. So if you look at it in a way, this diamond structure, which can be, we can visualize because they are sharing atom relationship with other atoms in the other cube. Similarly, there'll be an atom here with, so it's kind of a structure with where we can take one cube or we can take the next cube as well. So they all will show repetitive structure, very precise repetitive structure. So why it becomes important for us? Because we plane of that cube, how many atoms are there? We need to precisely know how many atoms are there, and we know. In different planes, we know exactly the number of atoms, and there are tables on that for silicon, for all silicon, all semiconducting materials. All right. Questions so far? This is something new, and we are getting a little bit deeper into terminology related to semiconductor materials. So then if silica or silicon occurs in, how do we get silicon out of it? So there are processes where we melt it, and we use a process where we have a kind of a pen type of seed structure, which is crystalline. We dip it into that molten silicon, we drag it out. When we drag it out, atoms start structure following that seed. What we get is a long cylinder like it's shown in this picture. Now, and once we get the cylinder, we cut it and we get those wafers. Now, this ingot word is they use in foundries, right? So ingot is big chunk of hot metallic or hard material that we can get out of. Saying that each different planes of that unit, like the crystalline structure. All right, let me see what. So let's see if I close my video, if that helps. Now, when we talk about this unit cell, and if you look at it, different unit cell atoms in there. So if I pick this plane, there are 5 atoms in there. But if I pick this plane, right? So if I pick maybe another plane, for example, I pick this guy, I take this plane, they have different number of atoms in there. So we use a way of identifying these from a thing called Miller indices. So there is a way how we identify which plane or which kind of semiconductor we are using. So what's written here, different crystalline planes, 100, 110, and 111 have different properties, right? So without going into how do we get these numbers, just think about plane signifies different, each of these set of 3 digits signifies different planes of that cube. And different planes would have different atoms in them, which would result into different electrical, different electronic, optical, and mechanical properties for those. All right, so far so good. Are we together on this so far?
Yes.
Can you hear me?
Yes, sir.
That's the question. Why do we need different crystalline planes exactly?
Can you guys hear me? All right.
Could you repeat some examples of crystalline
Because they
planes?
would have different number of atoms depending on our application.
Okay.
10, looking at this structure, and that's why I was saying don't go into more detail. We can go into more detail. What I want you to just see, if I pick this plane there, and this is same like this, there are 5 atoms in this plane, right? But if I pick this plane, which is diagonally crossing in the center of the cube, for example, that would mean if I take this plane, that would have a different number of atoms in there. This plane, and I'm just showing you, let me pick different colors so you can see the difference between different planes. So I can pick this plane also and make my device out of this plane. Cube at an angle. That would have different number of atoms in there. Atoms would mean different distances between those atoms and different forces between those atoms. And when you apply voltage, different conductivity properties through that plane. One plane properties would be different from another plane. Right? Okay, let's continue, because we'll talk about planes when we talk about wafers. So and what are the properties we talk about when we look at different planes for those. All right, so now this big cylindrical thing, ingot, we chop it into small pieces, and this ingot is, so we get something which is a rough kind of a cylinder. We use anywhere from, again, 2-inch to 16-inch wafers. This 12 inches is old slide, but current industry standard is 16-inch wafers. Now, when you chop it off, it's just a very shiny, silvery plate, right? I told you, we call it, think of it like a very thin plate, but it has no writing on it, right? Just silvery or mirrory kind of thing. Or what type of doping is there? We do what we call flats. We put some flat areas on the periphery of these wafers that come out of this. Those, that primary flat would mean the wafer is 111 p-type. So that 111 is specific plane out of that crystalline structure. If you get a wafer which has big flat and then a secondary small flat, that would mean it's 111 n-type. So there's terminology. I don't want to go into detail. It's a whole long list of what kind of flat would mean what kind of wafer is that. All right. So there are two main methods how we get these pure silicon crystalline structure. One is called Czochralski. This is written C-Z-O-C-H-A. Czochralski, named after some scientist who came up with that process. I don't know of this, how we would do that. So we start with starting material, which is silicon or silicon dioxide mixture. We heat it, do distillation, do reduction, remove oxide. We get polyclinic, melt again, and left hand side is just showing that big overview. On the right hand side is the picture of an actual process where we would melt silicon and this crucible. The crucible is hot, thing. We take the coils, the I have no idea what happened here. I apologize for this. I can blame it on the machine. Sorry about that. I don't know what happened. This is so embarrassing. Living in, oh, I can tell you, I have traveled around the world. You know, where's the worst signals I get? USA is the worst in communication. Let's get okay now. Is it better? Is it worse?
So your voice is still lagging. We didn't understand the last part you were saying. I just got it. The word signals comes in USA. Is that what you said?
Just said, yeah. All right. Do we take 5 minutes break? Let me restart everything and see if this makes it any better.
Okay, sure, sir.
Can you guys hear me now? Or is it still bad?
As if your sentences lag, and at times at times they're lagging.
Hear it. I don't. All right, so let's have 2 more slides I wanted to go over, and then we'll stop the live feed, and then we can talk. Maybe that's causing it. All right, let's out of it. All right, stop. Everyone, get your video feed going so I can see some visual feedback from you guys. All right, crystal growth. So we melt it and we put the seed, and the seed is the crystalline silicon material that we have, pure silicon. We have saved it. We dip it, and those crystal seeds are very expensive. We dip it and we draw it out. So our speed draw, because then what it does is it brings big cylinder of crystalline material with it. And that's the ingot. We lay it down, we polish it. So this is the, again, bunch of processes that happen. We lay it down, we polish the outside, and then each wafer undergoes a bunch of steps. I don't even know these steps, we use the wafers. But I know from etching, these are some things which are very standard. Etching is, we dip it in a solution that can etch it, right? Like an acid that can eat away the substrate. We polish it, so there are special machines where we use very high-end chemicals, which we call them slurries. So slurry is used to grind the surface and make it really, really smooth. Once we do that, we end up with wafers. That's on the, starting from raw silicon or silicon dioxide to get a silicon wafer. Once you have the silicon wafer, then let me show you silicon wafers. I have them here. Just bear with me, I'll show you the wafers. So here are the silicon wafers. So now let me see if my background is messing up my video. So you can see silicon. Oh, this is not shiny. And in the lab, we don't touch them with bare hand because they have a bunch of chemicals on them. But here are some more. So So here's the silicon wafer. See, let me switch off my background so you can see how it actually would be. All right, so you can see it's very shiny. I can see that. So and it's very thin. It's 0.5 millimeter thin. And we put them in specialized cassettes. We don't put them in. So you see there are a bunch of, they have pure gold in them, by the way. We did some process. Somehow they were waste. So maybe we etched it or something. So that's the semiconducting material on which the whole world is running network now. Right. My back vanity wall. All right, questions.